Let's begin our journey not with the sun itself, but with the vast cosmic landscape that existed before our star was even a possibility. Picture, if you will, a universe already ancient by the time our sun would form. We're travelling back roughly 5 billion years to a time when the universe was already 8 billion years old. The cosmos had already witnessed the birth and death of countless stars, each one contributing to the grand cosmic story that would eventually lead to our own star's creation. In this ancient universe, galaxies were already well established, having formed from the primordial hydrogen and helium created in the Big Bang. Our own galaxy, the Milky Way, was already a mature spiral galaxy, though perhaps not quite as organised as we see it today. Its spiral arms were regions of intense star formation, where gravity compressed vast clouds of gas and dust into the nurseries of new stars. The location where our sun would eventually form was at this time simply a region of space within one of these spiral arms. Known today as the Orion Arm, or sometimes the Local Arm, this region sits between two major spiral features of our galaxy. It's neither at the crowded centre of the galaxy, where stellar interactions are frequent and potentially destructive, nor at the sparse outer edges, where heavy elements necessary for planet formation are scarce. This positioning would prove crucial for the development of life as we know it. Too close to the galactic centre, and the intense radiation from the supermassive black hole and the dense stellar population would make stable planetary systems unlikely. Too far out, and there wouldn't be enough heavy elements, what astronomers call metals, to form rocky planets like Earth. The space that would become our solar system was part of a much larger structure called a giant molecular cloud. These clouds are among the most massive objects in our galaxy, containing enough material to form thousands or even millions of stars. They're called molecular clouds because the hydrogen within them exists primarily as molecules rather than individual atoms, a state that only occurs when the gas is cold and dense enough for atoms to bond together. This particular cloud, our sun's birthplace, was a turbulent, dynamic environment. Imagine a structure hundreds of light years across, containing gas and dust at temperatures barely above absolute zero. Within this frigid expanse, gravity was constantly at work, pulling material together in some regions while turbulence and magnetic fields worked to keep it apart in others. The cloud was not uniform, but filled with dense knots and filaments, regions where the material was slightly more concentrated than in surrounding areas. These molecular clouds don't exist in isolation. They're constantly being influenced by their surroundings. Stellar winds from nearby stars push against their boundaries. Ultraviolet radiation from hot, young stars heats their edges, causing gas to expand and sometimes escape. Supernovae, the explosive deaths of massive stars, send shockwaves rippling through them, compressing some regions while dispersing others. The chemical composition of this cloud was crucial for what would come next. While hydrogen and helium still made up the vast majority of its mass, about 98%, the remaining 2% consisted of heavier elements. These elements, everything from carbon and oxygen to iron and beyond, were the ashes of previous generations of stars. Each atom of carbon, each grain of silicon dust, had been forged in the nuclear furnace of a star that lived and died before our sun was born. This enrichment with heavy elements is what astronomers call metallicity, and it's a crucial factor in planet formation. The very first stars in the universe, formed from pristine hydrogen and helium, could never have formed planets like Earth. They lacked the raw materials, but by the time our sun's birth cloud existed, the galaxy had been enriched by billions of years of stellar evolution. Within this cloud, the process that would eventually lead to our sun's birth was already underway, though incredibly slowly. Gravity was gradually pulling material together, But this process alone would have taken far longer than the age of the universe to form a star. Something needed to give the cloud a push, to trigger the rapid collapse that leads to star formation. That trigger could have come from several sources. Perhaps it was the shock wave from a nearby supernova, compressing part of the cloud beyond the point where its internal pressure could resist gravity. Or it might have been the collision with another molecular cloud, creating regions of enhanced density. Some astronomers suggest it could have been the spiral density wave of our galaxy passing through, the same wave that helps maintain the spiral structure of the Milky Way. Whatever the specific trigger, we know that approximately 4,600,000,000 years ago, a particular region of this molecular cloud began to collapse more rapidly than its surroundings. This region, perhaps a few light years across, contained enough mass to form not just one star, but likely dozens or hundreds. Our sun would not be born alone, but as part of a stellar nursery, surrounded by siblings that would eventually disperse across the galaxy. As this region collapsed, it fragmented. Turbulence within the cloud, combined with its rotation and magnetic fields, caused it to break apart into smaller, denser cores. Each of these cores would become the seed of a new star or stellar system. The core that would become our sun was just one among many, distinguished only in retrospect by the remarkable system of planets it would eventually host. This collapsing core was still enormous by human standards, perhaps a light year or more across, and containing more mass than our entire current solar system. As gravity pulled this material inward, the cloud began to heat up. This might seem counterintuitive, as we often think of space as cold, but the compression of gas always generates heat. It's the same principle that makes a bicycle pump warm when you use it, but on a cosmic scale. The collapse wasn't uniform. The cloud was rotating, slowly at first, but as it contracted, that rotation sped up, just as a figure skater spins faster when pulling in their arms. This rotation would eventually determine the plane in which our planets orbit. The combination of gravity pulling inward and rotation creating an outward force began to flatten the cloud, transforming it from a roughly spherical shape into something more like a disk. At the center of this disk, where the density was highest and the temperature was rising most rapidly, the seeds of our sun were taking shape. This central region, what astronomers call a protostar, was not yet a true star. Nuclear fusion hadn't begun. Instead, it was glowing from the heat of gravitational compression alone, a process called Kelvin-Helmholtz contraction. The environment around this forming star was chaotic. Gas and dust swirled in complex patterns, driven by gravity, rotation, magnetic fields, and the increasing heat from the center. Jets of material began shooting out from the poles of the rotating disk, carrying away excess angular momentum and allowing more material to fall onto the growing protostar. These jets, which can extend for light years, are a common feature of star formation and serve as cosmic beacons marking the birth of new stars. The disk surrounding the protostar, what we call a protoplanetary disk, was where the raw materials for our planets were gathering. Different materials condensed at different distances from the forming star, depending on temperature. Close in, only metals and rocks could remain solid. Further out, where it was cooler, ices could form. This temperature gradient would eventually determine the basic architecture of our solar system, with rocky planets close to the sun and gas giants further out. As more and more material fell onto the protostar, its core temperature continued to rise. The pressure at the center became unimaginable, millions of times greater than anything we experience on Earth. Atoms were stripped of their electrons, creating a plasma, a fourth state of matter beyond solid, liquid, and gas. The naked nuclei of hydrogen atoms were being pressed closer and closer together, approaching the conditions necessary for nuclear fusion. This process of collapse and heating continued for millions of years. The protostar went through various stages, sometimes accumulating material steadily, sometimes in dramatic bursts as large clumps fell in from the surrounding disk. Each infalling piece of material added to the growing star's mass and angular momentum, contributing to the complex dynamics of the forming system. The molecular cloud that gave birth to our Sun was also forming other stars simultaneously. These stellar siblings of our Sun were going through their own formation processes, some faster, some slower, depending on their mass. The most massive stars in the cluster formed quickly and began producing intense ultraviolet radiation that started to clear away the remaining gas in the region. This clearing process would eventually limit how large our Sun could grow and would disperse the stellar nursery, sending each new star on its own path through the galaxy. The transformation from a collapsing cloud of gas to a true star is one of the most fundamental processes in the universe. And for our Sun, this metamorphosis occurred approximately 4,600,000,000 years ago. The exact moment when our Sun became a star, when nuclear fusion first ignited in its core, was not a sudden flash, but rather a gradual awakening that took place over thousands of years. Deep within the protostar that would become our Sun, conditions were approaching a critical threshold. The temperature at the core had risen to nearly 10 million degrees Celsius, and the pressure was billions of times greater than Earth's atmospheric pressure at sea level. Under these extreme conditions, hydrogen nuclei, simple protons, were moving so fast that when they collided, they could overcome their natural electromagnetic repulsion. This repulsion exists because protons are positively charged, and like charges repel each other. Under normal conditions, this repulsion is insurmountable, but at the temperatures and pressures in the protosun's core, protons were moving fast enough that they could get close enough for another force to take over, the strong nuclear force. This force, which only operates at incredibly short distances, is powerful enough to bind protons together, despite their electromagnetic repulsion. The specific fusion process that began in our young Sun is called the proton-proton chain. It starts with two protons colliding with such force that one of them transforms into a neutron through a process called beta plus decay, releasing a positron and a neutrino. The proton and neutron bind together to form deuterium, a heavy isotope of hydrogen. This first step is actually the slowest and most difficult part of the entire fusion process, which is fortunate for us, as it means our Sun burns its fuel slowly and steadily, rather than all at once. Once deuterium is formed, the fusion process accelerates. A deuterium nucleus quickly fuses with another proton to form helium-3, a light isotope of helium with two protons and one neutron. Then two helium-3 nuclei collide and fuse, producing helium-4, the common form of helium, and releasing two protons back into the stellar core to participate in future reactions. The net result of this complex dance of particles is that four hydrogen nuclei are converted into one helium nucleus, with the small difference in mass converted into pure energy according to Einstein's famous equation. This energy, initially in the form of gamma rays, begins its long journey from the core of the Sun to its surface, a journey that will take hundreds of thousands of years. As fusion began to generate energy in the core, the young Sun entered a critical phase of its development. The outward pressure from fusion energy began to counteract the inward pull of gravity. This balance between gravity trying to collapse the star and fusion pressure trying to expand it is called hydrostatic equilibrium, and it's what defines a true star. Our Sun had crossed the threshold from protostar to main sequence star. The establishment of this equilibrium didn't happen instantly. The young Sun went through a period of adjustment, with fusion rates fluctuating as the star found its balance. Sometimes fusion would produce too much energy, causing the core to expand and cool slightly, which would slow the fusion rate. Then gravity would compress the core again, raising the temperature and increasing fusion. Through these oscillations, the Sun gradually settled into a stable configuration. During this early phase, our Sun was actually about 30% less luminous than it is today. This might seem counterintuitive for a young star, but it makes sense when you consider the Sun's internal structure. The young Sun had a slightly different internal organisation, with convection zones extending deeper into its interior. As the Sun has aged and converted hydrogen to helium in its core, the core has become denser and hotter, gradually increasing the Sun's energy output over billions of years. The protoplanetary disk surrounding the young Sun was dramatically affected by the star's new energy outputs. The inner regions of the disk were heated to thousands of degrees, vaporizing dust grains and driving volatile compounds outward. This created a snowline in the disk, a distance beyond which water and other volatiles could condense into solid ice. Inside this line, only rocky and metallic materials could survive in solid form. The young Sun also began producing a stellar wind, a stream of charged particles flowing outward from its surface. In its youth, this wind was much stronger than it is today, perhaps hundreds of times more intense. This powerful wind began clearing away the remaining gas in the inner solar system, setting the stage for planet formation. The Sun's magnetic field, generated by the motion of charged particles in its interior, was also much more active in its youth. This led to frequent and powerful solar flares, explosive releases of magnetic energy that could dwarf anything we see from the Sun today. These flares would have bathed the early solar system in intense radiation, further sculpting the protoplanetary disk and affecting the chemistry of forming planets. As the Sun settled into its main sequence life, the protoplanetary disk around it was evolving rapidly. Within this disk, dust grains were colliding and sticking together, gradually building larger and larger objects. This process, called accretion, would eventually lead to the formation of planets. But in these early days, the disk was populated by countless small bodies, from microscopic dust grains to mountain-sized planetesimals. The temperature gradient in the disk, established by the Sun's heat, created distinct zones where different types of planets could form. Close to the Sun, where temperatures were highest, only materials with high melting points could remain solid. Iron, nickel, and various rocky minerals dominated this region. This is why the inner planets of our solar system, Mercury, Venus, Earth, and Mars, are primarily rocky bodies with iron cores. Further from the Sun, beyond the snowline, ice could exist alongside rock and metal. This additional solid material meant that larger planetary cores could form in this region. These cores, once they reached a critical mass, could gravitationally capture hydrogen and helium gas from the disk, growing into the gas giants we see today. Jupiter and Saturn formed in this way, accumulating massive gaseous envelopes around their solid cores. The young Sun's activity had profound effects on this planet formation process. Solar wind and radiation pressure pushed lighter elements outward, enriching the outer solar system with volatile compounds, while leaving the inner solar system relatively dry. Periodic increases in solar activity could have temporarily cleared gaps in the disk, affecting where and how planets formed. The Sun's gravity also played a crucial role in shaping the disk. Gravitational resonances, locations where orbital periods form simple ratios, created regions of stability and instability in the disk. These resonances influenced where planets could form stable orbits, and may have been responsible for gaps in the asteroid belt and the current orbital configurations of the planets. During this early period, the Sun was still surrounded by its stellar siblings, the other stars that formed from the same molecular cloud. These nearby stars influenced the early solar system through their gravity and radiation. Some astronomers believe that a close encounter with one of these sibling stars might have been responsible for disturbing the outer regions of our solar system, perhaps explaining the unusual orbits of some distant objects. The stellar nursery environment was both nurturing and dangerous for the young sun and its forming planetary system. On one hand, the presence of massive stars in the cluster meant that the region was enriched with heavy elements from stellar winds and supernovae. On the other hand, these same massive stars produced intense radiation that could strip away planetary atmospheres and truncate protoplanetary disks. Within a few million years of the Sun's birth, the most massive stars in its birth cluster began to die. These stars, perhaps 10 or 20 times the mass of our Sun, burned through their nuclear fuel quickly and exploded as supernovae. These explosions would have sent shockwaves through the young solar system, possibly triggering instabilities in the protoplanetary disk, but also enriching it with freshly synthesized heavy elements. Evidence for these nearby supernovae comes from meteorites, which contain decay products of short-lived radioactive isotopes that could only have been produced in a supernova and incorporated into our solar system shortly after. These isotopes, particularly aluminum-26 and iron-60, provide a radioactive clock that helps us date events in the early solar system. As the stellar nursery dispersed, driven apart by stellar winds and supernova, the young sun began its independent journey through the galaxy. No longer surrounded by its siblings, the Sun and its growing family of planets were now a solitary system, orbiting the galactic centre once every 230 million years. The Sun's early years set patterns that would persist for billions of years. The fusion processes established in its core would continue, slowly converting hydrogen to helium and releasing the energy that makes life on Earth possible. The balance between gravity and fusion pressure would maintain the Sun's stability, allowing it to shine steadily for billions of years to come. Following its dramatic birth and the ignition of nuclear fusion in its core, our young Sun entered a period of profound adjustment and development that would span several 100 million years. This era, while the Sun had achieved stellar status, was marked by dramatic variability and intense activity that would seem alien compared to the relatively calm star we observe today. The young Sun, now properly classified as a main sequence star, was still finding its equilibrium. Though fusion had begun in its core, the star's internal structure was still evolving, seeking the most efficient configuration for energy transport from the core to the surface. This process involved the development and refinement of distinct layers within the Sun, each with its own characteristics and method of moving energy outward. In these early years, the Sun rotated much faster than it does today. While our current Sun takes about 25 days to complete one rotation, at its equator, the young Sun probably spun around in just a few days. This rapid rotation had profound effects on the star's magnetic field, making it far more powerful and dynamic than what we observe now. The combination of fast rotation and vigorous convection in the Sun's outer layers created a magnetic dynamo of extraordinary strength. This powerful magnetic field manifested itself in spectacular ways. The young Sun's surface was covered with star spots, similar to today's sunspots, but far more numerous and extensive. Some of these spots might have covered 10% or more of the Sun's visible surface, compared to less than 1% during even the most active periods today. These massive spot complexes would have made the young Sun appear distinctly mottled if viewed from a distance, quite different from the relatively uniform disk we see now. The magnetic activity drove powerful stellar flares that would dwarf anything in recorded human history. These flares, explosive releases of magnetic energy, could release as much energy in minutes as the entire Sun produces in hours today. They sent streams of charged particles racing through the solar system at significant fractions of the speed of light, accompanied by intense bursts of X-rays and ultraviolet radiation. These superflares had important consequences for the developing solar system. They produced a stellar wind hundreds of times stronger than today's solar wind, a torrent of charged particles that helped clear away the remaining gas from the protoplanetary disk. This clearing process was essential for allowing the solid bodies in the disk to collide and merge without being slowed by gas drag, facilitating the growth of planetesimals into planets. The intense ultraviolet radiation from the young sun also played a crucial role in processing materials in the inner solar system. This radiation could break apart molecules and trigger chemical reactions, creating new compounds and altering the composition of dust grains and early planetary surfaces. Some scientists believe this early UV processing might have been important for creating organic molecules, the building blocks of life. Despite its violent activity, the young sun was actually dimmer than it is today, producing only about 70% of its current energy output. This apparent paradox, an active but dim young star, is explained by the sun's internal evolution. The core, where fusion occurs, was less dense and slightly cooler than it is now, resulting in a lower fusion rate. Over billions of years, as helium ash accumulated in the core, it would become denser and hotter, gradually increasing the sun's luminosity. This lower luminosity of the young sun presents an interesting puzzle known as the faint young sun paradox. Geological evidence shows that Earth had liquid water on its surface very early in its history, yet with the sun producing 30% less energy, Earth should have been frozen solid. Scientists have proposed various solutions, including a thicker atmosphere with more greenhouse gases on early Earth, or perhaps the young sun losing mass more rapidly than expected, which would have made it slightly more luminous. The sun's mass loss in its youth was indeed significant. The powerful stellar wind carried away not just particles, but also angular momentum, gradually slowing the sun's rotation. This process, called magnetic braking, would continue for hundreds of millions of years, eventually bringing the sun's rotation period to its current, more sedate pace. As the rotation slowed, the magnetic field weakened and the sun's activity level decreased. During this early period, the sun was still clearing its orbital path around the galaxy. The region of space through which the young solar system moved contained more gas and dust than it does today. Encounters with interstellar clouds could have affected the outer reaches of the solar system, compressing the heliosphere, the bubble of solar influence, and allowing more cosmic rays to penetrate into the inner solar system. The young sun's variability extended to its energy output as well. While the average luminosity was lower than today, it fluctuated significantly on various timescales. Short-term variations due to flares and the rotation of large spot groups could change the sun's brightness by several percent over days or weeks. Longer-term variations, possibly related to changes in the sun's internal structure or magnetic field generation, might have caused fluctuations over years or decades. These fluctuations in solar output would have created a challenging environment for any early life that might have been developing on Earth or elsewhere in the solar system. Periods of intense activity could have stripped away atmospheric gases from close-in planets, while quieter periods might have allowed atmospheres to rebuild. This cosmic weather would have been a major factor in planetary evolution. The composition of the solar wind was also different in the sun's youth. With more frequent and powerful flares, the wind carried a higher proportion of heavy ions, atoms stripped of many or all of their electrons. These heavy ions, when they impacted planetary surfaces or atmospheres, could cause different types of chemical reactions than the primarily hydrogen and helium wind of today. Inside the Sun, the core was gradually changing as hydrogen fused into helium. This process was slow but inexorable, with about 600 million tons of hydrogen converted to helium every second. The helium, being denser than hydrogen, sank toward the very center of the core, beginning the formation of what would eventually become a helium-rich core surrounded by a hydrogen-burning shell. The energy generated in the core faced a long and tortuous journey to the surface. In the innermost region, the radiative zone, energy moved outward as photons, particles of light. But the interior of the Sun is so dense that photons cannot travel far before being absorbed and re-emitted by atoms. A single photon's random walk from the core to the edge of the radiative zone could take hundreds of thousands of years. Above the radiative zone, in the convective zone, energy transport shifted to a different mechanism. Here, the temperature gradient became steep enough that convection, the physical movement of hot gas upward and cool gas downward, became more efficient than radiation for moving energy. Giant convection cells, some as large as Earth, carried hot plasma from the bottom of the convection zone to the surface, where it cooled and sank back down. The boundary between the radiative and convective zones, called the tachocline, is thought to be crucial for generating the Sun's magnetic field. The differential rotation between these zones, with the radiative zone rotating as a solid body and the convective zone rotating differentially, creates shear that stretches and amplifies magnetic field lines. As the young Sun evolved, its impact on the surrounding protoplanetary disk was profound. The inner edge of the disk was pushed outward by the increased radiation and stellar wind, creating a relatively clear region close to the star. This inner clearing is why Mercury, the innermost planet, orbits at a distance where it receives intense solar radiation, rather than being engulfed by the Sun itself. The disk itself was undergoing rapid evolution during this period. Dust grains were growing through collisions and sticking, forming larger and larger aggregates. When these aggregates reached sizes of about a kilometre, they became large enough that their own gravity became significant, accelerating their growth by attracting smaller particles. These kilometre-sized bodies, called planetesimals, were the building blocks of planets. In the inner solar system, where the young Sun's heat had driven away most volatile compounds, planetesimals were composed primarily of rock and metal. Their collisions were often violent, shattering both bodies or resulting in mergers that built larger objects. The energy from these collisions often melted the impacting bodies, allowing heavy metals to sink to the centre and lighter rocks to rise to the surface, a process called differentiation. Further from the Sun, beyond the snow line, where water ice could exist, planetesimals contained a mixture of rock and ice. This additional solid material allowed them to grow larger than their inner solar system counterparts. Some of these icy planetesimals grew large enough to gravitationally capture hydrogen and helium from the surrounding disk, becoming the cores of gas giant planets. The young Sun's radiation played a crucial role in determining the final masses of the planets. Once the Sun cleared away the gas disk, planet growth essentially stopped. This clearing happened relatively quickly, within about 10 million years of the Sun's formation. Planets that hadn't reached their full size by this time were left as smaller bodies like Mars, which appears to be an embryonic planet that never grew to its full potential. The Sun's early activity also influenced the delivery of water and organic compounds to the inner planets. While the inner solar system was initially dry, water and other volatiles were delivered by impacts from comets and asteroids that formed in the outer solar system. The young Sun's variable activity could have affected the orbits of these bodies, influencing when and how much water was delivered to planets like Earth. To truly understand our Sun, we must journey into its interior, exploring the intricate layers and regions that work in concert to produce the light and heat that sustain life on Earth. The sun's structure, refined over billions of years, represents a delicate balance of forces and processes that transform matter into energy on a scale that defies human comprehension. Beginning at the very heart of our star, we encounter the core, a sphere roughly 150,000 kilometers in diameter, about 20% of the sun's total radius. Yet within this relatively small volume, conditions exist that are found nowhere else in our solar system. The temperature here reaches 15 million degrees Celsius, hot enough that atoms cannot exist in their normal state. Instead, electrons are stripped from their nuclei, creating a plasma so dense that a teaspoon of core material would weigh about 150 grams on Earth, roughly 8 times denser than gold. The pressure at the sun's center is incomprehensible, about 250 billion times Earth's atmospheric pressure at sea level. Under these extreme conditions, hydrogen nuclei are forced close enough together to overcome their mutual electromagnetic repulsion and fuse into helium. This fusion process is remarkably inefficient on an individual particle basis, which is actually fortunate for us. A specific proton in the sun's core might wait billions of years before successfully fusing with another. This inefficiency means the sun burns its fuel slowly and steadily, rather than exploding like a hydrogen bomb. The fusion reactions in the core follow several pathways, but the dominant one in our sun is the proton-proton chain we discussed earlier. Every second, the core converts about 4 million tons of matter into pure energy. This might sound like rapid consumption, but the sun contains so much hydrogen that it can maintain this rate for billions of years. Currently, after 4.5 billion years of fusion, the sun has converted only about 100 Earth masses of hydrogen into helium, a tiny fraction of its total mass. The helium produced by fusion doesn't immediately leave the core. Being heavier than hydrogen, it tends to accumulate in the center, gradually building up a helium-rich region. This accumulation has important consequences for the sun's future evolution. As the helium concentration increases, the core becomes denser, which paradoxically makes it hotter and increases the fusion rate. This is why the sun is slowly becoming more luminous over geological time. Surrounding the core is the radiative zone, extending from about 20% of the sun's radius to 70%. In this region, energy from the core moves outward primarily through radiation, though calling it movement might be generous given how slowly it proceeds. The radiative zone is so dense that photons cannot travel more than about a millimeter before being absorbed by an atom and then re-emitted in a random direction. This absorption and re-emission process means that energy takes an extraordinarily long time to cross the radiative zone. A photon created in a fusion reaction in the core might take anywhere from 10,000 to 170,000 years to reach the outer edge of the radiative zone, following a random zigzagging path that covers millions of times the straight-line distance. During this journey, the high-energy gamma rays produced by fusion are gradually converted into lower-energy photons, eventually becoming the visible light we see. The temperature in the radiative zone decreases steadily with distance from the core, falling from about 7 million degrees Celsius at its inner boundary to about 2 million degrees at its outer edge. This temperature gradient is crucial for maintaining the outward flow of energy. If the gradient becomes too steep, the region becomes unstable to convection, which is exactly what happens at the outer boundary of the radiative zone. At about 70% of the sun's radius, we encounter a critical transition called the tachocline. This thin layer, perhaps only a few percent of the sun's radius in thickness, marks the boundary between the radiative zone and the convective zone above it. The tachocline is more than just a boundary. It's thought to be the birthplace of the sun's magnetic field. The radiative zone below rotates essentially as a solid body, while the convective zone above rotates differentially, with the equator spinning faster than the poles. This shear at the tachocline stretches and amplifies magnetic field lines, contributing to the Sun's magnetic dynamo. Above the tachocline lies the convective zone, extending from 70% of the Sun's radius to the visible surface. Here, the temperature gradient becomes so steep that radiation alone cannot efficiently transport energy. Instead, energy moves via convection, with hot plasma rising to the surface, cooling, and then sinking back down. This process is similar to water boiling in a pot, but on a stellar scale. The convection in this zone is not uniform, but organized into cells of various sizes. The largest cells, called giant cells, may extend through the entire convective zone and take months to complete one circulation cycle. Smaller cells, called supergranules, are about 30,000 kilometers across and last for about a day. At the surface, we can directly observe the smallest convection cells, called granules, which are about 1,000 kilometers across and last only minutes. These convection patterns do more than just transport energy. They also generate acoustic waves that propagate through the Sun. These sound waves, though far below the frequency humans can hear, cause the entire Sun to vibrate like a ringing bell. By studying these vibrations through a technique called helioseismology, scientists can probe the Sun's interior structure, much as geologists use seismic waves to study Earth's interior. The visible surface of the Sun, what we call the photosphere, is not a solid surface but rather the layer where the Sun becomes opaque to visible light. Below this level, the Sun is so dense that light cannot escape directly. Above it, the density drops rapidly enough that light can travel freely into space. The photosphere is remarkably thin, only about 500 kilometers thick, less than 1,000th of the Sun's radius. The temperature of the photosphere averages about 5,700 degrees Celsius, cool enough that some simple molecules can exist. We can observe absorption lines from these molecules in the Sun's spectrum, providing information about the Sun's composition and physical conditions. The photosphere is also where we observe sunspots, regions where strong magnetic fields inhibit convection, causing the surface to cool and appear dark against the brighter surrounding areas. Above the photosphere lies the chromosphere, a layer about 2,000 kilometers thick where something puzzling occurs. While we might expect the temperature to continue decreasing with altitude, it instead begins to rise, reaching about 20,000 degrees Celsius at the top of the chromosphere. This heating is thought to be caused by magnetic waves and small-scale magnetic reconnection events, though the exact mechanisms are still being studied. The chromosphere is normally invisible, overwhelmed by the brightness of the photosphere below. However, during total solar eclipses, when the moon blocks the photosphere, the chromosphere becomes visible as a reddish ring around the Sun's edge. This red colour comes from hydrogen atoms emitting light at specific wavelengths, particularly the hydrogen alpha line that gives the chromosphere its name, which means colour sphere. Above the chromosphere, we encounter a thin transition region where the temperature skyrockets from 20,000 to over 1 million degrees Celsius in just a few hundred kilometres. This dramatic temperature increase remains one of the great mysteries in solar physics. How can the temperature increase so dramatically as we move away from the Sun's energy source? The answer likely involves the complex interaction of magnetic fields, waves, and plasma dynamics. Beyond the transition region extends the corona, the Sun's outer atmosphere, reaching millions of kilometers into space. The corona is incredibly hot, with temperatures ranging from 1 to 3 million degrees Celsius, and in some regions associated with solar flares exceeding 10 million degrees. The corona's extreme temperature gives its particles enough energy to escape the Sun's gravity, creating the solar wind that flows throughout the solar system. Despite its high temperature, the corona is so tenuous that it contains less heat energy than the cooler but denser photosphere below. If you could somehow survive the radiation and place your hand in the corona, you wouldn't feel hot because there are so few particles to transfer heat to your skin. The corona's structure is dominated by the sun's magnetic field. Magnetic field lines emerging from the sun's surface shape the corona into complex patterns of loops, streamers, and holes. Coronal loops are closed magnetic field lines that trap hot plasma, creating bright arcing structures visible in extreme ultraviolet and X-ray images. Coronal streamers are larger structures that extend far into space, often visible during solar eclipses as pearly white features stretching away from the sun. Coronal holes are regions where magnetic field lines are open, extending into interplanetary space rather than looping back to the sun's surface. These regions appear dark in X-ray and ultraviolet images because the plasma can escape along the open field lines, reducing the density. The high-speed solar wind, travelling at speeds up to 800 kilometers per second, originates from these coronal holes. The boundary between the corona and interplanetary space is not sharp but gradual. The solar wind carries the sun's magnetic field with it, creating what we call the interplanetary magnetic field. This field, frozen into the flowing plasma, forms a spiral pattern throughout the solar system due to the combination of the wind's outward flow and the sun's rotation, like water from a rotating garden sprinkler. At a distance of about 10 solar radii from the sun's centre, the solar wind becomes supersonic, exceeding the speed at which waves can propagate through the plasma. This transition marks the beginning of the wind's journey through the solar system, carrying particles, magnetic fields, and energy to the furthest reaches of the sun's influence. The sun's magnetic field, generated deep within its interior, threads through all these layers, connecting the core to the corona and beyond. This field is not static but constantly evolving, twisted by differential rotation, stretched by convection, and reconfigured by reconnection events. The field's complexity increases from the relatively organized field in the radiative zone to the tangled dynamic field in the convection zone and atmosphere. Understanding the sun's structure also means appreciating the various timescales on which different processes operate. In the core, fusion reactions happen in fractions of a second, but the random walk of photons through the radiative zone takes hundreds of thousands of years. Convection cells in the outer layers turn over in minutes to months, while the overall magnetic cycle takes about 11 years. The sun's gradual evolution as it ages operates on a timescale of billions of years. The sun's structure also exhibits fascinating asymmetries and variations. The rotation rate varies not just with latitude, but also with depth, a phenomenon called differential rotation. The magnetic field strength varies dramatically from place to place and time to time. Even the shape of the sun isn't perfectly spherical, it's slightly oblate due to its rotation, though the difference between its equatorial and polar diameters is only about 10 kilometers. Temperature variations across the sun's surface, though small in percentage terms, are significant in absolute terms. Sunspots can be 1,500 degrees cooler than the surrounding photosphere, while solar flares can create regions millions of degrees hotter than the typical corona. These variations drive complex flows and waves throughout the sun's atmosphere. The density changes throughout the sun are even more dramatic than the temperature variations. From the core's density of 150 grams per cubic centimetre, greater than any element on Earth, to the corona's density of only about 10 billion particles per cubic centimetre, millions of times less dense than Earth's atmosphere at sea level, the sun encompasses an extraordinary range of physical conditions. The sun's structure is maintained by a delicate balance of forces. Gravity constantly tries to collapse the sun, while pressure from hot gas and radiation pushes outward. Magnetic forces add another layer of complexity, sometimes supporting material against gravity in prominences, sometimes accelerating particles to near light speed in flares. The balance between these forces has remained stable for billions of years, but it's a dynamic stability, constantly adjusting to small perturbations. Energy transport through the sun involves all three mechanisms known to physics: radiation, convection, and conduction. Radiation dominates in the inner 70%, convection in the outer 30%, and while conduction is generally negligible due to the sun's high temperature, it becomes important in certain situations, such as in the thin transition region between the chromosphere and corona. The chemical composition also varies throughout the sun, though not as dramatically as the physical conditions. The core is becoming enriched in helium as hydrogen fuses, while the outer layers maintain roughly their original composition. Heavy elements, though only about 2% of the sun's mass, play crucial roles in opacity and energy transport, making the sun's structure sensitive to their exact abundances and distributions. The sun operates as a vast cosmic engine, converting matter into energy through processes that exemplify the fundamental forces of nature. Every second of every day for the past 4.5 billion years, this stellar machinery has functioned with remarkable consistency, maintaining the delicate balance that makes life on Earth possible. To understand how the sun works, we must explore not just its structure, but the dynamic processes that drive its continuous operation. At the most fundamental level, the sun is powered by nuclear fusion, specifically the conversion of hydrogen into helium. But this simple statement masks the extraordinary complexity of what actually occurs. The fusion process in the sun's core involves a series of nuclear reactions, particle interactions, and energy transformations that showcase the elegant interplay of all four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The primary fusion mechanism in our sun, the proton-proton chain, begins with an almost impossibly unlikely event. Two protons must collide with enough energy to overcome their electromagnetic repulsion and get close enough for the weak nuclear force to convert one proton into a neutron. This conversion, called beta plus decay, releases a positron and a neutrino. The probability of this happening in any single collision is so small that an individual proton in the sun's core might wait billions of years before successfully participating in this reaction. This inefficiency is actually crucial for the sun's stability. If fusion were easier, stars would burn through their fuel quickly and explosively. The difficulty of this first step acts as a natural thermostat. If the core gets slightly hotter, fusion rates increase, producing more energy, which causes the core to expand and cool, reducing the fusion rate. If the core cools slightly, fusion slows, gravity compresses the core, heating it up and increasing fusion again. This negative feedback loop maintains remarkable stability over billions of years. Once the first step produces deuterium, the subsequent reactions proceed much more quickly. Deuterium fuses with another proton to form helium-3, and then two helium-3 nuclei combine to produce helium-4 plus 2 protons. The net result converts 4 hydrogen nuclei into one helium nucleus, with the mass difference converted to energy according to Einstein's mass-energy equivalence. The energy released in each complete fusion cycle amounts to about 26.7 million electron volts. While this might seem large, it's actually tiny on a macroscopic scale. The power density in the sun's core, the amount of energy produced per unit volume, is only about 276 watts per cubic metre, comparable to the heat generated by a compost pile. The Sun produces so much total energy, not because fusion is incredibly intense, but because the core is incredibly large. The energy produced by fusion initially appears as high-energy gamma rays. These photons begin their journey outward, but the path from core to surface is anything but straightforward. In the dense interior of the Sun, photons cannot travel far before interacting with matter. They're constantly absorbed and re-emitted, scattered and redirected in a random walk that gradually carries them outward. During this journey, the photons undergo a gradual transformation. Each interaction with matter tends to produce multiple lower energy photons from a single higher energy one. Gamma rays become X-rays, which become ultraviolet light, which eventually becomes the visible light we see. This process, called thermalization, ensures that by the time energy reaches the Sun's surface, it's in a form that can travel through space and warm planets rather than destroying them with gamma radiation. The neutrinos produced in fusion have a very different journey. These ghostly particles interact so weakly with matter that they zip straight out of the Sun at nearly the speed of light, reaching Earth in just over 8 minutes. Every second, about 65 billion solar neutrinos pass through every square centimetre of Earth's surface. The detection and study of these neutrinos provides direct information about fusion reactions happening in the Sun's core right now. Unlike light, which tells us about conditions hundreds of thousands of years ago, the Sun's energy production is remarkably steady but not perfectly constant. Small variations in the fusion rate do occur, influenced by changes in core temperature, density, and composition. As helium accumulates in the core over billions of years, the core gradually contracts and heats up, causing a slow increase in the Sun's luminosity. The Sun today is about 30% brighter than it was when it first formed. Beyond the core, energy transport mechanisms showcase fascinating physics. In the radiative zone, photons carry energy outward, but the process is incredibly slow due to the high opacity of the solar material. The opacity depends on temperature, density, and composition in complex ways. Heavier elements, despite being only a small fraction of the Sun's mass, contribute significantly to opacity, affecting how quickly energy can escape. The transition from radiative to convective energy transport occurs where the temperature gradient becomes too steep for radiation alone to carry the energy flux. This condition, called the Schwarzschild criterion, depends on the relationship between temperature, pressure, and opacity. When this criterion is met, the plasma becomes unstable to convection, and bulk motion of material becomes the dominant energy transport mechanism. Convection in the Sun is a magnificent display of fluid dynamics on a stellar scale. Hot plasma rises from the bottom of the convection zone, carrying energy upward. As it rises, it expands and cools, eventually becoming denser than its surroundings and sinking back down. This creates a continuous circulation pattern that efficiently transports energy to the surface. The convective motions are not smooth or uniform, but highly turbulent. Turbulence creates a cascade of eddy sizes, from giant cells that span significant fractions of the convection zone down to tiny vortices that dissipate into heat. This turbulence plays crucial roles in mixing material, generating acoustic waves, and contributing to the Sun's magnetic field generation. The Sun's magnetic field is generated through a process called a dynamo, where the motion of electrically conducting fluid converts kinetic energy into magnetic energy. In the Sun, this happens primarily at the tachocline, where the differential rotation between the radiative and convective zones creates strong shear. This shear stretches and amplifies magnetic field lines, while convective motions twist and tangle them. The magnetic field generated in the interior doesn't stay there. Magnetic buoyancy causes strong field concentrations to rise through the convection zone, eventually emerging at the surface as active regions. These emergences follow patterns related to the Sun's 11-year magnetic cycle, appearing first at mid-latitudes and then progressively closer to the equator as the cycle progresses. Once magnetic fields emerge through the photosphere, they create a wide variety of phenomena. Sunspots form where strong magnetic fields inhibit convection, reducing the local temperature and creating dark regions. The magnetic fields in sunspots are typically 3,000 times stronger than Earth's magnetic field, strong enough to affect the motion of charged particles dramatically. Solar flares occur when magnetic field lines become so twisted and stressed that they suddenly reconfigure, releasing enormous amounts of energy in minutes. The reconnection process converts magnetic energy into kinetic energy, heating plasma to tens of millions of degrees and accelerating particles to near light speed. A large flare can release as much energy as billions of hydrogen bombs exploding simultaneously. Coronal mass ejections represent another dramatic manifestation of the Sun's magnetic activity. These events launch billions of tons of plasma into space at speeds exceeding 1,000 kilometers per second. The ejected material carries magnetic field with it, creating a magnetic cloud that can trigger geomagnetic storms when it reaches Earth. The solar wind itself is a continuous manifestation of how the Sun works. The corona's high temperature gives particles enough kinetic energy to escape the Sun's gravity. The wind carries not just particles, but also magnetic field, angular momentum, and energy throughout the solar system. The wind's properties vary with solar activity, location on the Sun, and the structure of the coronal magnetic field. The Sun also generates an enormous spectrum of waves and oscillations. Acoustic waves, essentially sound waves, propagate through the solar interior, causing the entire Sun to vibrate in millions of different modes simultaneously. These oscillations, typically with periods of about 5 minutes, provide information about the Sun's internal structure through helioseismology. Magnetic waves of various types propagate through the Sun's magnetized plasma. Alphen waves, where magnetic field lines oscillate like plucked strings, may play a crucial role in heating the corona. Magnetosonic waves combine magnetic and pressure forces. These waves can transport energy from the interior to the atmosphere, contributing to the heating and dynamics of the upper layers. The Sun's rotation adds another layer of complexity to how it operates. Different parts of the Sun rotate at different rates, with the equator completing a rotation in about 25 days, while the poles take about 35 days. This differential rotation continuously shears magnetic field lines, contributing to the dynamo process and the solar cycle. The solar cycle itself is a fundamental aspect of how the Sun works. Every 11 years, the Sun's magnetic field reverses polarity, with the north and south magnetic poles switching places. This cycle drives variations in sunspot numbers, flare frequency, and coronal structure. The cycle is thought to arise from the interaction between differential rotation, convection, and magnetic fields, though many details remain uncertain. Energy loss from the Sun occurs through multiple channels. Most energy escapes as electromagnetic radiation, predominantly visible light but spanning from radio waves to gamma rays. About 2% of the energy emerges as neutrinos. A tiny fraction goes into the kinetic energy of the solar wind. The Sun also loses angular momentum through the magnetized wind, causing its rotation to gradually slow over billions of years. The relationship between our Sun and Earth represents one of the most crucial partnerships in the known universe, at least from our perspective, as living beings who depend on this cosmic dance for our very existence. This partnership, refined over 4.5 billion years, involves complex interactions across the 93 million miles of space that separate our planet from its parent star. Every square metre of Earth's surface facing the Sun receives about 1,361 watts of solar energy, a value known as the solar constant, though it's not truly constant but varies slightly with solar activity and Earth's orbital distance. This energy drives virtually every process on Earth's surface, from weather and ocean currents to photosynthesis and the water cycle. Without the Sun's continuous energy input, Earth would be a frozen, lifeless ball of rock with a surface temperature approaching absolute zero. The Sun's energy reaches Earth primarily as electromagnetic radiation, with about 43% in the visible light spectrum that our eyes evolved to detect, about 49% as near-infrared radiation that we feel as heat, and about 7% as ultraviolet radiation. This energy spectrum is crucial for life as we know it. Visible light powers photosynthesis, the process by which plants convert solar energy into chemical energy, forming the base of most food chains on Earth. Photosynthesis is perhaps the most important biological process linking the Sun and Earth. Plants, algae, and certain bacteria capture photons and use their energy to convert carbon dioxide and water into glucose and oxygen. This process not only provides food for most life on Earth, but also maintains the oxygen in our atmosphere. Every breath we take contains oxygen molecules that were produced by photosynthesis, powered by sunlight. The Sun drives Earth's climate system through differential heating. Because Earth is a sphere, solar energy strikes different latitudes at different angles. The equator receives direct sunlight year-round, while the poles receive oblique sunlight that must pass through more atmosphere. This uneven heating creates temperature gradients that drive atmospheric circulation, creating trade winds, jet streams, and weather patterns that distribute heat around the globe. Ocean currents, too, are ultimately powered by the Sun. Solar heating causes water to evaporate, increasing the salinity and density of the remaining seawater in some regions. Temperature differences create density gradients that, combined with wind patterns, drive the global ocean circulation system. The Gulf Stream, for instance, transports warm water northward, moderating temperatures in Western Europe and making regions like the British Isles much warmer than other locations at similar latitudes. The water cycle itself is a solar-powered process. The Sun's energy evaporates about 434,000 cubic kilometres of water from Earth's surface each year. This water vapour rises, cools, condenses into clouds, and eventually falls as precipitation, providing fresh water for terrestrial life. Without the Sun's energy input, the water cycle would cease, and Earth's water would remain frozen or stagnant. But the Sun's influence on Earth extends far beyond just providing light and heat. The solar wind, that stream of charged particles flowing from the Sun's corona, interacts with Earth's magnetic field to create the magnetosphere, a protective bubble that shields us from harmful cosmic radiation. Without this magnetic shield, the solar wind would gradually strip away Earth's atmosphere, as appears to have happened to Mars billions of years ago. The interaction between the solar wind and Earth's magnetosphere creates some of nature's most spectacular displays, the auroras. When solar wind particles are funneled along magnetic field lines toward Earth's poles, they collide with atmospheric gases, causing them to emit light. Oxygen produces green and red auroras, while nitrogen creates blue and purple displays. These lights have fascinated humans throughout history, inspiring countless myths and legends. Solar storms can dramatically affect this Sun-Earth interaction. Coronal mass ejections can compress Earth's magnetosphere, triggering geomagnetic storms that can disrupt satellite communications, damage power grids, and increase radiation exposure for astronauts and airline passengers on polar routes. The Carrington event of 1859, the largest geomagnetic storm in recorded history, caused telegraph systems worldwide to fail, with some telegraph operators receiving electric shocks and telegraph paper catching fire. The sun's ultraviolet radiation plays a crucial role in maintaining Earth's ozone layer. UV light splits oxygen molecules in the upper atmosphere, allowing them to recombine as ozone. This ozone layer then absorbs harmful UV radiation, protecting life on the surface from DNA damage that could cause mutations and cancer. It's a self-regulating system, where the sun both creates the threat and provides the shield. Earth's atmosphere itself is profoundly shaped by solar radiation. The thermosphere, the layer above about 80 kilometers altitude, is heated directly by solar X-rays and ultraviolet radiation, reaching temperatures over 1,000 degrees Celsius during high solar activity. This heating causes the atmosphere to expand, increasing drag on satellites and affecting their orbits. Satellite operators must account for solar activity when planning missions and maintaining orbital positions. The sun's gravitational influence keeps Earth in its orbit, providing the stable conditions necessary for life to evolve and thrive. Earth's nearly circular orbit means that the amount of solar energy received varies by only about 6% throughout the year. This orbital stability, maintained for billions of years, has allowed life to develop complex adaptations to relatively predictable seasonal cycles. Earth's axial tilt of 23.5 degrees, combined with its orbit around the Sun, creates the seasons that profoundly influence life on our planet. As Earth orbits the Sun, different hemispheres receive more direct sunlight, creating summer and winter cycles. These seasonal variations drive migration patterns, breeding cycles, hibernation, and countless other biological rhythms that structure ecosystems worldwide. The Sun has also influenced Earth's geological evolution. Solar heating drives weathering and erosion, breaking down rocks and redistributing materials across the planet's surface. Temperature variations cause rocks to expand and contract, contributing to their breakdown. The sun-driven water cycle is the primary agent of erosion, carving valleys, transporting sediments, and shaping landscapes over millions of years. Fossil fuels, which have powered human civilization for the past 2 centuries, represent ancient solar energy stored in chemical form. Coal formed from plants that captured solar energy hundreds of millions of years ago. Oil and natural gas formed from marine organisms that lived in ancient oceans, also powered by solar energy through photosynthesis. In burning fossil fuels, we're releasing solar energy captured long ago, along with carbon dioxide that's affecting our modern climate. The sun's influence on Earth's climate extends over various timescales. The 11-year solar cycle causes small variations in the total solar irradiance reaching Earth, contributing to short-term climate variability. Longer-term variations in solar activity, such as the Maunder minimum from 1645 to 1715, when sunspots were extremely rare, may have contributed to the Little Ice Age, though the exact relationship between solar activity and climate remains an active area of research. Earth's ice ages are influenced by variations in its orbit around the Sun, known as Milankovitch cycles. These include changes in orbital eccentricity over 100,000 years, axial tilt variations over 41,000 years, and precession of the equinoxes over 26,000 years. These cycles affect the distribution and intensity of solar radiation reaching Earth, triggering the advance and retreat of ice sheets. The sun has been crucial in the evolution of life on Earth. Early photosynthetic organisms transformed Earth's atmosphere from one dominated by carbon dioxide to one rich in oxygen, fundamentally changing the planet's chemistry and enabling the evolution of complex life. The daily cycle of sunlight and darkness established circadian rhythms that regulate biological processes in almost all organisms, from bacteria to humans. Vision, one of the most important senses for many organisms, evolved in response to the sun's light. Eyes have evolved independently dozens of times, each adapted to detect and process electromagnetic radiation in the visible spectrum. The specific wavelengths our eyes detect correspond to the peak output of the sun and the wavelengths that penetrate Earth's atmosphere and water most effectively. Plants have evolved elaborate mechanisms to track and respond to the sun. Phototropism causes plants to grow toward light, maximizing their exposure to solar energy. Some plants, like sunflowers, exhibit heliotropism, following the sun's path across the sky throughout the day. These adaptations demonstrate the fundamental importance of solar energy to life on Earth. The sun's energy has also shaped animal behavior and evolution. Many animals use the sun for navigation, from bees that use polarized light patterns to navigate back to their hives, to birds that use the sun's position, along with other cues for migration. Desert animals have evolved behaviors and physiologies to cope with intense solar radiation, while polar animals have adapted to extreme variations in day length. Human civilization has been profoundly influenced by our relationship with the sun. Agriculture, the foundation of civilization, depends on understanding and working with solar-driven seasons. Ancient monuments like Stonehenge appear to be aligned with solar events like solstices, suggesting our ancestors' deep awareness of the sun's importance. Solar calendars have structured human societies for millennia, organizing agricultural activities, religious festivals, and social life. In modern times, we're learning to harness solar energy directly through photovoltaic cells and solar thermal systems. These technologies convert sunlight into electricity or heat, providing renewable energy that doesn't contribute to climate change. As we face the challenges of global warming, largely caused by releasing ancient solar energy stored in fossil fuels, we're turning back to direct solar energy as a sustainable solution. The sun also poses challenges for our technological civilization. Solar flares and coronal mass ejections can damage satellites, disrupt communications, and even threaten power grids on Earth. As we become more dependent on technology, we become more vulnerable to space weather. Understanding and predicting solar activity has become crucial for protecting our technological infrastructure. The sun, far from being a steady, unchanging orb, exhibits a remarkable variety of dynamic phenomena that can affect the entire solar system. These events, ranging from the regular rhythm of the solar cycle to explosive flares that release enormous amounts of energy in minutes, showcase the complex interplay of magnetic fields, plasma physics, and nuclear processes that govern our star's behavior. The most fundamental pattern in solar activity is the 11-year solar cycle, discovered through centuries of patient observation. This cycle represents a complete reversal of the sun's magnetic field, with the magnetic north and south poles switching places. The cycle begins at solar minimum, when sunspots are rare, and the sun's magnetic field resembles a simple dipole, similar to a bar magnet. As the cycle progresses towards solar maximum, the magnetic field becomes increasingly complex and tangled, producing numerous sunspots, flares, and other active phenomena. Sunspots, those dark blemishes on the solar surface, are perhaps the most visible manifestation of solar magnetic activity. These regions, which can be larger than Earth, appear dark because they are about 1500 degrees Celsius cooler than the surrounding photosphere. The cooling occurs because intense magnetic fields, typically 3,000 times stronger than Earth's magnetic field, inhibit the convective transport of heat from below. Sunspots usually appear in pairs or groups, with each spot representing a location where magnetic field lines either emerge from or return to the solar interior. The leading spot in a group, leading in the direction of solar rotation, typically has opposite magnetic polarity from the trailing spot. Interestingly, this polarity pattern is opposite in the Sun's northern and southern hemispheres and reverses with each solar cycle. The number and distribution of sunspots follow predictable patterns. At the beginning of a solar cycle, spots appear at latitudes around 30 degrees north and south of the equator. As the cycle progresses, new spots form progressively closer to the equator, creating a pattern known as the butterfly diagram when plotted over time. This pattern reflects the underlying dynamics of the Sun's magnetic dynamo. Individual sunspots have complex structures and life cycles. A typical spot begins as a small pore, a dark area without the characteristic surrounding penumbra. If it continues to grow, it develops a dark central umbra surrounded by a lighter penumbra with radial filamentary structure. Large sunspots can persist for weeks or even months, rotating with the sun and sometimes surviving multiple rotations. Within sunspots, we observe fascinating phenomena that reveal the complex interaction between magnetic fields and plasma. Umbral dots, bright points within the dark umbra, represent locations where hot gas manages to penetrate the strong magnetic field. Light bridges, bright structures that sometimes divide the umbra, show where the magnetic field has weakened enough to allow convection. The penumbra exhibits the Evershed effect, an outward flow of gas at speeds of several kilometers per second. Solar flares represent one of the most dramatic phenomena on the Sun. These explosive events occur when magnetic field lines become so twisted and stressed that they suddenly reconfigure, releasing enormous amounts of energy. A large flare can release 10 to the 25th power joules of energy, equivalent to billions of hydrogen bombs exploding simultaneously. The process that triggers flares, called magnetic reconnection, occurs when oppositely directed magnetic field lines come close together and merge, forming a new field configuration. This process converts magnetic energy into kinetic energy, heating plasma to tens of millions of degrees and accelerating particles to near light speed. The accelerated particles spiral along magnetic field lines, producing intense radiation across the electromagnetic spectrum. Flares are classified according to their X-ray brightness, with categories A, B, C, M and X representing increasing intensity. Each category is 10 times more powerful than the previous one, and within each category, a numerical scale from 1 to 9 provides finer gradation. The most powerful flare ever recorded on November 4, 2003 was initially classified as X28, but was later estimated to be about X45. The effects of solar flares extend far beyond the Sun itself. The intense electromagnetic radiation reaches Earth in about 8 minutes, causing immediate effects on the ionosphere. Radio communications can be disrupted, especially at high frequencies. GPS signals can be degraded. The enhanced ionization can increase atmospheric drag on satellites, affecting their orbits. Flares often trigger coronal mass ejections, though the two phenomena are distinct and can occur independently. A coronal mass ejection, or CME, involves the expulsion of billions of tons of plasma and magnetic field from the Sun's corona. These massive clouds of magnetized plasma travel through interplanetary space at speeds ranging from 200 to 3,000 kilometers per second. The structure of a CME is complex, often resembling a giant magnetic flux rope with helical field lines. As the CME travels through space, it expands, sometimes becoming larger than the Sun itself. When a CME is directed toward Earth, we see a characteristic halo pattern in coronagraph images, as the ejection expands around the Sun from our perspective. When a CME reaches Earth, typically 1 to 3 days after leaving the Sun, it can trigger a geomagnetic storm. The CME's magnetic field interacts with Earth's magnetosphere, causing it to compress on the day side and stretch on the night side. If the CME's magnetic field is oriented opposite to Earth's, the interaction is particularly strong, allowing solar wind particles to penetrate deep into the magnetosphere. Geomagnetic storms can have significant technological impacts. They induce electric currents in long conductors like power lines, potentially damaging transformers and causing blackouts. The March 1989 geomagnetic storm caused a 9-hour blackout in Quebec, affecting millions of people. Satellites can be damaged by energetic particles or experience increased drag as the atmosphere expands. Astronauts may need to take shelter from increased radiation, but geomagnetic storms also create beautiful auroral displays, visible at latitudes much lower than usual. During extreme storms, auroras have been seen as far south as the Caribbean. The colours and patterns of auroras depend on the altitude and type of atmospheric gas being excited by incoming particles. Green, the most common colour, comes from oxygen at altitudes around 100 kilometres. Solar prominences represent another spectacular solar phenomenon. These structures consist of relatively cool, dense plasma suspended in the hot, tenuous corona by magnetic fields. Quiescent prominences can remain stable for weeks or months, appearing as dark filaments when viewed against the solar disk, or as bright arcing structures when seen at the limb. The plasma in prominences is typically 100 times denser and 100 times cooler than the surrounding corona, yet it remains suspended against gravity by magnetic forces. The magnetic field configuration supporting a prominence is complex, often involving twisted flux ropes or arcade structures. When the magnetic field becomes unstable, prominences can erupt, sometimes triggering CMEs. The solar wind itself exhibits considerable variation in structure. The fast solar wind, originating from coronal holes, travels at speeds up to 800 kilometers per second and has a relatively steady flow. The slow solar wind, coming from the vicinity of coronal streamers, moves at 300 to 400 kilometers per second and is more variable in density and composition. The boundary between fast and slow wind streams creates corrotating interaction regions that spiral through the solar system as the Sun rotates. When fast wind catches up with slow wind, it creates a compression region with enhanced magnetic field and particle density. These structures can trigger geomagnetic activity when they reach Earth, though typically less severe than CME-driven storms. Coronal holes, regions where the Sun's magnetic field lines are open to interplanetary space, are another important solar phenomenon. These regions appear dark in X-ray and extreme ultraviolet images because the plasma can escape along open field lines, reducing the density. Coronal holes can persist for many solar rotations, creating recurring patterns of geomagnetic activity as Earth repeatedly encounters the high-speed stream. The Sun also produces various types of waves and oscillations. Morton waves, named after their discoverer, are shock waves that propagate across the solar surface at speeds of about 1,000 kilometers per second, visible as arc-shaped fronts in hydrogen alpha images. EIT waves, observed in extreme ultraviolet, are similar phenomena that may represent the coronal response to explosive events. Coronal waves can travel across the entire solar disk, compressing and heating plasma as they go. These waves provide information about the corona's magnetic field, strength and structure. Some waves are trapped in coronal loops, oscillating back and forth and gradually damping, providing a tool for coronal seismology. Solar tornadoes, rotating columns of plasma in the solar atmosphere, showcase another type of dynamic phenomenon. These structures, which can be as wide as Earth and extend tens of thousands of kilometers high, rotate at speeds up to 300,000 kilometers per hour. Unlike terrestrial tornadoes, solar tornadoes are shaped by magnetic fields rather than pressure differences. Microflares and nanoflares, tiny versions of solar flares, occur constantly on the Sun. While individually much less energetic than major flares, they're so numerous that they might contribute significantly to coronal heating. Detecting and studying these small events pushes the limits of current solar telescopes. The Sun's polar regions exhibit unique phenomena. The polar magnetic fields reverse at solar maximum, but not simultaneously. There can be periods when the Sun effectively has two north poles or two south poles. Polar crown filaments, prominences that form at high latitudes, mark the boundary between the polar field and the lower latitude active regions. Jets and spicules represent small-scale dynamic phenomena that occur constantly on the Sun. Spicules are fountain-like jets of plasma that shoot up from the chromosphere into the corona at speeds of about 20 to 100 kilometers per second. Millions of spicules exist at any moment, potentially playing a role in heating the corona and feeding the solar wind. Humanity's relationship with observing and understanding the Sun spans from prehistoric times to our current age of space-based telescopes and sophisticated computer models. This journey of discovery reflects not just our growing scientific knowledge, but also the deep cultural and practical importance the Sun has held for every human civilization. The earliest humans undoubtedly noticed the Sun's daily journey across the sky and its seasonal variations. Archaeological evidence suggests that prehistoric peoples tracked the Sun's movement with surprising accuracy. Sites like Newgrange in Ireland, built around 3200 BCE, feature passages aligned with the winter solstice sunrise. Stonehenge, constructed in stages between 3000 and 1500 BCE, aligns with both summer and winter solstices, suggesting sophisticated understanding of the Sun's annual cycle. Ancient civilizations developed elaborate mythologies and religious systems centered on the Sun. The ancient Egyptians worshipped Ra, the sun god who sailed across the sky in his solar bark and travelled through the underworld at night. They observed that the Sun's path varied throughout the year and used this knowledge to predict the flooding of the Nile, crucial for agriculture. Egyptian obelisks served as primitive sundials, tracking time through the movement of shadows. The ancient Greeks made significant advances in understanding the Sun's nature and motion. Anaxagoras, in the 5th century BCE, proposed that the Sun was a giant flaming ball of metal, larger than the Peloponnese Peninsula, a radical idea that contributed to his exile from Athens. Aristarchus of Samos, in the 3rd century BCE, attempted to measure the relative distances to the Sun and Moon using geometric methods during lunar eclipses, concluding correctly that the Sun was much farther away and larger than the Moon. Greek philosophers also grappled with explaining solar eclipses. Thales of Miletus allegedly predicted a solar eclipse in 585 BCE, though the method he used remains unknown. By the time of Ptolemy in the 2nd century CE, Greek astronomers had developed sophisticated geometric models that could predict eclipses with reasonable accuracy, even though their Earth-centered cosmology was fundamentally incorrect. Chinese astronomers maintained detailed records of solar observations for over 2,000 years. They recorded sunspots as early as 28 BCE, describing them as dark blemishes on the sun's face. Chinese records mention observations of sunspots visible to the naked eye, which requires spots covering about 1/10,000th of the sun's visible surface. These ancient records provide valuable data about long-term solar activity patterns. The Chinese also developed sophisticated methods for predicting eclipses, crucial for the emperor's legitimacy as the son of heaven. Court astronomers who failed to predict eclipses could face execution, providing strong motivation for accurate observations and calculations. The Chinese recognized the cyclical nature of eclipses and developed tables to predict their occurrence, though their models were based on empirical patterns rather than physical understanding. Mayan astronomers in Mesoamerica created remarkably accurate solar calendars, tracking the solar year to within minutes of its actual length. The Dresden Codex, one of only 4 surviving Mayan books, contains detailed eclipse tables that could predict solar eclipses centuries in advance. Mayan architecture often incorporated solar alignments, with buildings and ceremonial spaces designed to mark solstices, equinoxes, and other significant solar events. Islamic astronomers during the medieval period made crucial contributions to solar observation. They refined measurements of the solar year's length and the obliquity of Earth's axis. Ibn al-Haytham, known in the West as al-Hazan, wrote extensively about optics and correctly explained that we see the moon and planets because they reflect sunlight. He also studied sunspots, describing observations made using a camera obscura technique. The invention of the telescope in the early 17th century revolutionized solar observation. Galileo Galilei began telescopic observations of sunspots in 1610, though he initially thought they might be planets transiting the sun. His detailed drawings showed that spots moved across the sun's disk, proving that the sun rotates. This observation challenged the prevailing Aristotelian view that the sun was perfect and unchanging. Galileo's sunspot observations led to a priority dispute with Christoph Scheiner, a Jesuit astronomer who also claimed to have discovered sunspots. This controversy reflected larger tensions between scientific observation and religious doctrine. The Catholic Church's position that celestial bodies were perfect and immutable was challenged by clear evidence of changing features on the sun's surface. Johannes Kepler made several important contributions to solar astronomy. He correctly explained the optics of the camera obscura, which became an important tool for safe solar observation. During the transit of Mercury in 1631, which he had predicted, astronomers realized that precise observations of planetary transits could be used to measure the solar system's scale. The transit of Venus in 1761 and 1769 prompted the first global scientific collaboration. Astronomers travelled to remote locations worldwide to observe these rare events, using the data to calculate the astronomical unit, the distance from Earth to the Sun. James Cook's first voyage to the Pacific included observations of the 1769 transit from Tahiti. William Herschel, famous for discovering Uranus, also made important solar observations. He incorrectly believed that the Sun might be inhabited, proposing that sunspots were openings in a luminous atmosphere, revealing a cooler, possibly habitable surface below. Despite this error, his systematic observations of solar activity contributed to understanding the Sun's variability. The discovery of the solar spectrum marked a turning point in solar physics. In 1802, William Hyde Wollaston noticed dark lines in the spectrum of sunlight, though he didn't understand their significance. Joseph von Fraunhofer independently discovered and catalogued these lines in 1814, mapping over 500 of them. These Fraunhofer lines would later prove crucial for understanding the Sun's composition. The connection between solar activity and terrestrial phenomena began to emerge in the 19th century. In 1843, Heinrich Schwabe announced his discovery of the sunspot cycle after 17 years of daily observations. He noticed that sunspot numbers varied with a period of about 10 years, later refined to 11 years. This was the first recognition of a regular pattern in solar activity. Richard Carrington's observations on September 1st, 1859, marked the first recorded observation of a solar flare. He was sketching sunspots when he witnessed an intense brightening that lasted about 5 minutes. 17 hours later, Earth experienced the most powerful geomagnetic storm in recorded history, with auroras visible in the tropics and telegraph systems failing worldwide. Carrington suggested a connection between the solar event and the geomagnetic storm, though this link wasn't widely accepted for decades. The invention of spectroscopy revolutionized solar astronomy. Gustav Kirchhoff and Robert Bunsen showed in 1859 that each element produces characteristic spectral lines. By comparing laboratory spectra with the Fraunhofer lines in sunlight, astronomers could determine the sun's chemical composition. This was remarkable. We could determine what the sun was made of without ever visiting it. The element helium was discovered on the sun before being found on Earth. During the 1868 solar eclipse, Jules Janssen and Norman Lockyer independently observed a bright yellow spectral line that didn't match any known element. Lockyer named this new element helium, from the Greek word helios for sun. Helium wasn't isolated on Earth until 1895. Photography transformed solar observation in the late 19th century. The first photograph of the sun was taken in 1845 by French physicists Hippolyte Fizeau and Léon Foucault. By the 1860s, routine photographic monitoring of the sun had begun. Warren de la Rue's photoheliograph produced daily images showing sunspot evolution, providing objective records that could be studied and compared over time. Spectroheliographs, invented independently by George Ellery Hale and Henri Deslandres in the 1890s, allowed astronomers to photograph the sun in specific wavelengths of light. This revealed structures invisible in white light, such as prominences and the chromosphere. Hale's observations at Mount Wilson Observatory led to his discovery in 1908 that sunspots have strong magnetic fields, the first detection of magnetic fields beyond Earth. The coronagraph, invented by Bernard Liot in 1930, allowed astronomers to observe the solar corona without waiting for total eclipses. By creating an artificial eclipse within the telescope, blocking out the bright solar disk, Liot could study the faint corona any clear day. This led to discoveries about coronal structure and the detection of coronal emission lines from highly ionized iron, revealing the corona's million-degree temperature. Einstein's theories of relativity provided new ways to test our understanding of the sun. The 1919 solar eclipse expedition, led by Arthur Eddington, confirmed that the sun's gravity bends starlight, validating general relativity. The perihelion precession of Mercury, which Newtonian gravity couldn't fully explain, was perfectly accounted for by Einstein's theory. The discovery of neutrinos and the development of neutrino detectors opened a new window on the sun. Raymond Davis Jr.'s experiment, starting in the 1960s, detected solar neutrinos, particles produced in fusion reactions in the sun's core. However, it found only about 1/3 the expected number, creating the solar neutrino problem that took decades to resolve. The solution neutrino oscillation revealed new physics and earned Davis the Nobel Prize. Radio astronomy, developed during and after World War II, revealed that the sun emits radio waves. Solar radio bursts associated with flares and other activity provided new ways to study solar phenomena. Radio observations could penetrate clouds, allowing continuous monitoring regardless of weather. Different radio frequencies originate from different heights in the solar atmosphere, providing three-dimensional information about solar structure. The space age transformed solar observation. Rockets and satellites could observe wavelengths blocked by Earth's atmosphere, particularly ultraviolet and X-ray radiation, crucial for understanding the corona and solar activity. The Orbiting Solar Observatory series, launched between 1962 and 1975, provided continuous observations of the Sun in ultraviolet and X-ray wavelengths. Skylab, America's first space station, carried a battery of solar telescopes called the Apollo Telescope Mount. Astronauts operated these instruments from 1973 to 1974, obtaining over 150,000 images of the Sun. Skylab observations revealed coronal holes, coronal mass ejections, and the complexity of the transition region between the chromosphere and corona. The Solar Maximum mission, launched in 1980, was designed to study the Sun during the peak of the solar cycle. Although it suffered a malfunction, it was repaired by Space Shuttle astronauts in 1984, the first satellite repair in orbit. SMM observed numerous flares and CMEs, advancing our understanding of solar explosive events. The Solar and Heliospheric Observatory, SOHO, launched in 1995, has provided continuous observations of the Sun for over 2 decades. Positioned at the L1 Lagrange point between Earth and Sun, SOHO monitors solar activity and provides early warning of Earth-directed CMEs. Its discoveries include solar tsunamis, coronal waves, and thousands of sun-grazing comets. The Transition Region and Coronal Explorer, TRACE, operated from 1998 to 2010, providing high-resolution images of the solar atmosphere. TRACE revealed the fine structure of coronal loops, the dynamics of solar flares, and the complexity of magnetic reconnection events. Its images, showing graceful arcing loops and explosive eruptions, captured public imagination. Japan's Hinode satellite, launched in 2006, carries instruments to study the Sun's magnetic field with unprecedented precision. Its observations have revealed the ubiquity of small-scale magnetic fields, the role of waves in coronal heating, and the triggers of solar eruptions. International collaboration allows continuous coverage as the satellite orbits Earth. The Solar Dynamics Observatory, launched in 2010, provides ultra-high-resolution images of the Sun every 12 seconds in multiple wavelengths. SDO has observed numerous flares, eruptions, and transits of planets across the Sun. Its continuous, high-quality data enables detailed studies of solar dynamics and space weather forecasting. The Parker Solar Probe, launched in 2018, is humanity's first mission to touch the Sun. Flying through the corona, it directly samples the solar wind and magnetic field near their source. Its observations are revolutionizing our understanding of coronal heating, solar wind acceleration, and the transport of energetic particles. The Daniel K. Inouye Solar Telescope in Hawaii, which began operations in 2020, is the world's largest solar telescope. With a 4-meter mirror, it can resolve features on the Sun as small as 30 kilometers across. Its first images showed convection cells the size of Texas, revealing unprecedented detail in the solar surface. Modern solar observation combines ground-based and space-based telescopes, each with unique advantages. Ground-based observatories can use larger telescopes and are easier to upgrade, while space telescopes avoid atmospheric distortion and can observe wavelengths blocked by the atmosphere. Computer networks link observatories worldwide, enabling continuous monitoring as Earth rotates. Citizen science now contributes to solar observation. Amateur astronomers monitor sunspot numbers, contributing to long-term datasets. Projects like Sunspotter engage the public in classifying sunspot complexity. During total solar eclipses, thousands of observers along the path of totality collect data on the corona's structure. Artificial intelligence and machine learning are transforming solar data analysis. These techniques can identify patterns in vast datasets, predict solar flares, and track features across multiple observations. AI helps process the enormous data volumes from modern solar telescopes, identifying events that might otherwise be missed. Our Sun, at 4.5 billion years old, has reached a stable middle age, roughly halfway through its expected main sequence lifetime. Like a person in their 40s who has settled into established patterns while remaining vibrant and active, the Sun has achieved a remarkable equilibrium between the competing forces within it, maintaining steady energy output while still exhibiting dynamic behaviour that continues to surprise and fascinate scientists. Today's Sun converts approximately 600 million tons of hydrogen into helium every single second through nuclear fusion. This might sound like rapid consumption, but the Sun's total mass is about 2 times 10 to the 30th power kilograms, so enormous that it can maintain this rate for billions of years to come. The energy released from this mass conversion follows Einstein's famous equation, producing about 3.8 times 10 to the 26th power watts of power, equivalent to nearly 1 trillion times Earth's current global energy consumption every second. The Sun's current luminosity has increased by approximately 30% since its birth, a gradual brightening that will continue throughout its remaining main sequence lifetime. This slow increase results from the accumulation of helium in the core, which makes the core denser and hotter, thereby increasing the rate of fusion reactions. The Sun today is about 4% more luminous than it was just 500 million years ago when complex life was first emerging on Earth. The solar constant, the amount of solar energy reaching Earth's orbit, currently measures about 1,361 watts per square metre, though this value fluctuates by about 0.1% over the 11-year solar cycle. These small variations, while seemingly minor, can influence Earth's climate patterns, affecting everything from hurricane formation to agricultural yields. Scientists continuously monitor these variations using satellites, building detailed records of the Sun's energy output. The Sun's current rotation exhibits complex patterns that vary with both latitude and depth. At the equator, the surface completes one rotation in approximately 25 days, while near the poles, rotation takes about 35 days. This differential rotation continuously shears and stretches magnetic field lines, contributing to the generation of the Sun's complex magnetic field. Below the surface, in the radiative zone, the Sun appears to rotate as a solid body with a period of about 27 days. Our Sun's magnetic field currently exhibits a well-organized structure during solar minimum, resembling a simple bar magnet with clear north and south poles. However, as we progress through the solar cycle toward maximum, this simple structure becomes increasingly complex, with multiple poles and tangled field lines creating active regions across the solar surface. The overall field strength at the poles measures about 1 to 2 Gauss, similar to a refrigerator magnet, but in sunspots field strengths can exceed 3000 Gauss. The current solar cycle, number 25 since systematic recording began, started in December 2019 and is expected to peak around 2025. Early indications suggest this cycle might be stronger than initially predicted, with sunspot numbers and solar activity exceeding forecasts. This reminds us that despite centuries of observation, the sun still holds surprises and our predictive capabilities remain limited. Modern observations reveal that the sun's surface, the photosphere, seethes with constant activity. Granulation cells, typically about 1,000 kilometers across, appear and disappear on timescales of 5 to 10 minutes. These cells represent the tops of convection columns, bringing hot gas up from below. Between the granules in the intergranular lanes, cooler gas descends back into the interior. This pattern covers the entire solar surface, creating a constantly shifting mosaic of bright cells and dark boundaries. Supergranulation, a larger-scale convection pattern, organizes the surface into cells about 30,000 kilometers across. These cells last for about a day and play a crucial role in organizing the sun's magnetic field. The boundaries between supergranulation cells concentrate magnetic field lines, creating the chromospheric network visible in certain wavelengths of light. The sun's atmosphere today displays remarkable complexity revealed by modern instruments. The chromosphere, normally invisible due to the photosphere's brightness, shows intricate structure when observed in specific wavelengths like hydrogen alpha. Spicules, jet-like features, constantly shoot upward from the chromosphere into the corona, each lasting only minutes, but collectively numbering in the millions at any given time. The transition region, where temperatures rise dramatically from about 20,000 to over 1 million degrees Celsius, remains one of the sun's most mysterious regions. This thin layer, only a few hundred kilometers thick, exhibits rapid variability and complex structure. Modern observations show that it's not a uniform layer, but rather a highly corrugated interface between the chromosphere and corona, shaped by magnetic fields and dynamic processes. The solar corona today extends millions of kilometers into space, its structure shaped entirely by magnetic fields. During solar minimum, the corona exhibits a relatively simple structure, with streamers concentrated near the equator and large coronal holes at the poles. As solar activity increases, the corona becomes more complex, with active regions, loops, and streamers appearing at all latitudes. The temperature of today's corona remains a major scientific puzzle. While the sun's surface is about 5,700 degrees Celsius, the corona reaches temperatures exceeding 1 million degrees and up to 10 million degrees in flaring regions. This temperature increase with distance from the heat source violates our intuitive understanding of thermodynamics. Current theories invoke magnetic waves, nanoflares, and magnetic reconnection as heating mechanisms, but the exact process remains debated. Solar wind continuously flows from today's sun, carrying about 1 million tons of material into space every second. This wind varies in speed and density depending on its source region. Fast wind from coronal holes travels at 700 to 800 kilometers per second, while slow wind from near streamers moves at 300 to 400 kilometers per second. This wind carries the sun's magnetic field throughout the solar system, creating the heliosphere that extends far beyond Pluto's orbit. The heliosphere, our sun's sphere of influence, currently extends about 120 astronomical units from the sun, where it meets the interstellar medium. The Voyager spacecraft have crossed this boundary, providing direct measurements of conditions where the solar wind finally succumbs to interstellar pressure. The heliosphere shields the solar system from about 70% of cosmic rays, high-energy particles from deep space. Today's sun produces various forms of radiation across the electromagnetic spectrum. In addition to visible light, it emits radio waves, infrared radiation, ultraviolet light, X-rays, and even gamma rays during flares. Each wavelength provides information about different layers and processes in the sun. Radio emissions tell us about the corona and solar wind, while X-rays reveal hot plasma in active regions and flares. The sun currently loses mass through two primary mechanisms. The solar wind carries away about 1 million tons per second, while the conversion of mass to energy in fusion removes about 4 million tons per second. Over the sun's lifetime, this mass loss totals less than 0.1% of its original mass, but it's enough to gradually increase Earth's orbital distance, currently by about 1.5 centimeters per year. Helioseismology reveals the sun's current internal structure with remarkable precision. Millions of acoustic oscillation modes continuously ring through the sun, created by convective motions near the surface. By analysing these oscillations, scientists can probe conditions throughout the solar interior, measuring the depth of the convection zone, the rotation rate at different depths, and even detecting sunspots on the far side of the sun before they rotate into view. The sun's current chemical composition reflects 4.5 billion years of nuclear processing. The core has become enriched in helium, now comprising about 60% of the core's mass, compared to essentially zero at the sun's birth. The outer layers retain their original composition, about 73% hydrogen, 25% helium, and 2% heavier elements. This composition gradient will become important during the sun's later evolution. Neutrinos streaming from the sun's core provide real-time information about current fusion reactions. Modern neutrino detectors observe about 65 billion solar neutrinos passing through each square centimetre of Earth every second. These ghostly particles, which barely interact with matter, carry information about conditions in the core that won't affect the sun's visible surface for hundreds of thousands of years. The sun's current impact on Earth's climate operates through multiple mechanisms. Total solar irradiance variations directly affect the amount of energy Earth receives. Solar ultraviolet variations influence stratospheric ozone and atmospheric chemistry. Solar particle events can trigger changes in atmospheric electricity and cloud formation. While these solar influences are smaller than human-caused climate change, they remain important for understanding natural climate variability. Space weather from today's sun poses increasing challenges for our technological civilization. Solar flares can disrupt radio communications and GPS navigation. Coronal mass ejections can damage satellites, threaten astronauts with radiation, and induce currents in power grids. As we become more dependent on technology, understanding and predicting space weather becomes increasingly critical. The sun's current activity affects satellite operations in multiple ways. Atmospheric drag on low Earth orbit satellites increases during solar maximum as enhanced ultraviolet radiation heats and expands the upper atmosphere. Energetic particles can cause single-event upsets in satellite electronics, requiring systems to be hardened against radiation. Differential charging from varying particle fluxes can cause electrical discharges that damage components. Modern solar observation capabilities far exceed anything available to previous generations. We monitor the sun continuously from space and ground-based observatories in wavelengths from radio to gamma rays. High-resolution imaging reveals features as small as a few tens of kilometers on the solar surface. Spectroscopy provides information about temperature, density, velocity, and magnetic fields throughout the solar atmosphere. Current research focuses on several key questions about our sun. What mechanisms heat the corona to such extreme temperatures? How can we better predict solar flares and coronal mass ejections? What drives the solar cycle's 11-year periodicity and longer-term variations? How does the sun's magnetic field generation really work? These questions drive the development of new observational capabilities and theoretical models. The sun today serves as our primary laboratory for understanding stellar physics. As the only star we can observe in detail. It provides ground truth for stellar models applied throughout the universe. Phenomena discovered on the Sun, from magnetic reconnection to convection patterns, inform our understanding of other stars, accretion disks, and even planetary magnetospheres. As we peer into the cosmic future, the story of our Sun becomes one of gradual transformation, punctuated by dramatic changes that will reshape the entire solar system. The Sun's remaining lifetime stretches billions of years ahead, a span of time so vast that it dwarfs the entire history of complex life on Earth. Yet this future is not uncertain or mysterious. The laws of stellar physics allow us to predict with remarkable precision how our star will evolve, age, and eventually die. Over the next billion years, the Sun will continue its inexorable brightening, increasing in luminosity by approximately 10%. This might seem like a modest change, but its effects on Earth will be profound. The additional solar energy will accelerate the weathering of silicate rocks, which removes carbon dioxide from the atmosphere. As CO2 levels drop, photosynthesis will become increasingly difficult. Within 600 million to 900 million years, carbon dioxide levels may fall below the threshold needed for C3 photosynthesis, used by most plants, including trees and crops. Some plants using C4 photosynthesis, which is more efficient at low CO2 concentrations, might persist longer, perhaps another 100 million years. But eventually, even these hardy plants will succumb to the lack of atmospheric carbon dioxide. The death of plant life will cascade through Earth's ecosystems, leading to the collapse of food chains and the extinction of most complex life forms. The age of abundant life on Earth, which has lasted for hundreds of millions of years, will draw to a close. As the Sun continues to brighten, Earth's surface temperature will rise dramatically. The increased solar heating will enhance water evaporation from the oceans, adding more water vapour to the atmosphere. Since water vapour is a powerful greenhouse gas, this will create a positive feedback loop, trapping more heat and causing further evaporation. Climate models suggest that within 1 to 1.5 billion years, Earth may enter a runaway greenhouse effect, similar to what happened to Venus billions of years ago. During this runaway greenhouse phase, Earth's oceans will begin to boil away. Water vapour will rise high into the atmosphere, where ultraviolet radiation from the Sun will break water molecules apart into hydrogen and oxygen. The light hydrogen will escape to space, permanently removing water from Earth. Within a few 100 million years of the runaway greenhouse beginning, Earth's oceans will be completely gone, leaving behind a dry, barren world with surface temperatures exceeding 400 degrees Celsius. Meanwhile, inside the Sun, fundamental changes will be occurring. As hydrogen in the core continues to fuse into helium, the core will become increasingly dominated by helium ash. This helium, being denser than hydrogen, will cause the core to contract slightly under its own gravity. The contraction will heat the core, accelerating fusion reactions and producing more energy. This is why the Sun grows brighter with age, a seemingly paradoxical situation where using up fuel makes a star more luminous. In approximately 5 billion years, the Sun will begin to exhaust the hydrogen fuel in its core. With about 10% of the Sun's total hydrogen converted to helium, the core will be almost entirely helium, surrounded by a shell where hydrogen fusion continues. This marks the end of the Sun's main sequence life and the beginning of its transformation into a red giant star. The transition from main sequence star to red giant is relatively rapid in astronomical terms, taking only a few 100 million years. As the core runs out of hydrogen, it will contract and heat up, while the outer layers of the Sun will begin to expand dramatically. The Sun's surface will cool as it expands, changing colour from yellow-white to orange and eventually to red, hence the term red giant. During the red giant phase, the the Sun will swell to enormous proportions. Current models suggest it will reach about 200 times its current diameter, extending past the current orbit of Venus and possibly engulfing Earth. Even if Earth's orbit expands due to the Sun's mass loss, our planet will likely be destroyed, either vaporized within the Sun's outer layers or stripped of its crust by the intense stellar wind. The red giant Sun will be a spectacular sight from the outer solar system. Despite its cooler surface temperature, its enormous size will make it about 2,000 times more luminous than today. The habitable zone, the region where liquid water can exist, will shift outward to the vicinity of Jupiter and Saturn. Some of the moons of these gas giants, such as Europa and Titan, might experience conditions suitable for liquid water on their surfaces for the first time. As a red giant, the Sun will experience significant mass loss through a greatly enhanced stellar wind. This wind, much stronger than today's solar wind, will carry away perhaps a quarter to a third of the Sun's total mass over the red giant phase. This mass loss will cause the planet's orbits to expand as the Sun's gravitational pull weakens. Mars might move outward by 20% or more, while the outer planets will drift even farther from the dying star. The Sun's time as a red giant will not be stable or quiet. It will experience thermal pulses, periods of unstable fusion that cause the star to brighten and dim over thousands of years. During these pulses, the Sun might vary in brightness by factors of 2 or more, dramatically affecting any remaining planets. Convection cells on the red giant Sun will be enormous, perhaps as large as the current orbit of Mercury, creating a mottled, constantly changing surface. After about 1 billion years as a red giant, the Sun's core will reach a critical point. The temperature and pressure will become sufficient to ignite helium fusion, a process called the helium flash. In a matter of seconds to minutes, helium fusion will begin throughout the core, producing an enormous amount of energy. However, this energy will be absorbed by the Sun's outer layers, so the helium flash won't be visible from outside. Following the helium flash, the Sun will settle into a new equilibrium, fusing helium into carbon and oxygen in its core, while hydrogen fusion continues in a surrounding shell. This phase, called the horizontal branch, will last about 100 million years. The Sun will shrink somewhat from its maximum red giant size and become slightly hotter, though still much larger and more luminous than today. Helium fusion produces carbon and oxygen through the triple alpha process, where 3 helium nuclei combine almost simultaneously. This process is much more temperature sensitive than hydrogen fusion, making the star less stable. Small temperature fluctuations cause large changes in energy production, leading to various forms of stellar pulsation and variability. When the helium in the core is exhausted, the Sun will face another crisis. Unlike more massive stars, the Sun lacks sufficient mass to ignite carbon fusion. The carbon-oxygen core will become inert, supported only by electron degeneracy pressure, a quantum mechanical effect that prevents further collapse. The Sun will enter its final red giant phase, called the asymptotic giant branch. During this asymptotic giant branch phase, the Sun will expand to its maximum size, possibly reaching beyond Earth's current orbit. It will consist of a dense carbon-oxygen core surrounded by helium and hydrogen fusion shells. These shells will burn unstably, causing thermal pulses every few thousand to tens of thousands of years. During each pulse, the Sun's luminosity might increase by factors of several thousand for brief periods. The thermal pulses will drive powerful stellar winds that strip away the Sun's outer layers. This mass loss will accelerate as the Sun evolves, eventually removing the entire envelope and exposing the hot core. The ejected material will form an expanding shell of gas around the dying star, glowing from the intense ultraviolet radiation from the exposed core. This beautiful structure is called a planetary nebula, though it has nothing to do with planets. The planetary nebula phase is brief, lasting only about 10,000 to 20,000 years. The nebula will expand at speeds of 20 to 30 kilometers per second, eventually dispersing into interstellar space. This ejected material, enriched with carbon, nitrogen and oxygen produced during the Sun's life, will eventually be incorporated into new generations of stars and planets. What remains of the Sun after the planetary nebula disperses will be a white dwarf, a stellar corpse about the size of Earth, but containing about half the Sun's original mass. This white dwarf will be incredibly dense, with a teaspoon of its material weighing about 5 tons. It will initially be extremely hot, perhaps 100,000 degrees Celsius at its surface, glowing white hot despite its small size. The white dwarf Sun will be composed primarily of carbon and oxygen, the ashes of helium fusion, surrounded by a thin layer of helium and possibly hydrogen. It will no longer produce energy through fusion, but will slowly cool by radiating away its stored heat. This cooling process is extraordinarily slow. The white dwarf will take billions of years to cool to the temperature of surrounding space. As the white dwarf cools, it will change colour from white to yellow to orange to red, eventually becoming a black dwarf, a cold, dark stellar remnant. However, the universe is not yet old enough for any black dwarfs to exist. Even the oldest white dwarfs are still warm enough to glow faintly. The Sun's final fate as a black dwarf lies trillions of years in the future, far longer than the current age of the universe. The planets that survive the Sun's red giant phases will continue orbiting the white dwarf, though in much wider orbits due to the Sun's mass loss. These frozen worlds will receive negligible heat from the dim white dwarf. Any planet that still retains an atmosphere will see it freeze and fall as snow onto the surface. The solar system will become a cold, dark place, illuminated only by distant stars. Interestingly, the white dwarf Sun might briefly host a new habitable zone very close to its surface. For perhaps a few million years after its formation, planets or asteroids orbiting within about 0.01 astronomical units might experience temperatures suitable for liquid water. However, any such habitable period would be fleeting as the white dwarf cools. The Sun's transformation will return much of its material to interstellar space. The solar wind during the red giant phase and the planetary nebula will release about half the Sun's mass back into the galaxy. This material, enriched with heavier elements produced during the Sun's life, will eventually be incorporated into new molecular clouds, contributing to future generations of stars and planets. The Sun's death will not be unique or unusual. Every day, countless stars similar to our Sun end their lives as white dwarfs. The galaxy is littered with these stellar corpses, each one a monument to a star that once shone brightly. Planetary nebulae, the beautiful death shrouds of sun-like stars, are common throughout the galaxy, their glowing shells visible in amateur telescopes. Understanding the Sun's future evolution helps us appreciate the cosmic context of our existence. Life on Earth exists during a special time in the Sun's history, when it is stable, middle-aged, and providing just the right amount of energy. This golden period won't last forever. In cosmic terms, complex life on Earth exists for only a brief moment in the Sun's 10 billion-year lifetime. The study of stellar evolution also reveals the interconnectedness of cosmic processes. The carbon in our bodies, the oxygen we breathe, and the nitrogen in our DNA were all created in stars that died before our Sun was born. When the Sun dies, it too will contribute these elements to future stellar generations. We are literally made of stardust, and to stardust we shall return.